As we saw in the previous example on the sandwiches, the fundamental counting principle is a way that allows us to find all the possible outcomes, given that we know the number of possible outcomes from each stage or event of an experiment. So in the situation above with the sandwiches, each event was the selection of the meat, cheese, and the bread. And simply by knowing the amount that each one of those occur and multiplying those three amounts together, we got the total number of possible outcomes for that experiment, the experiment of selecting the sandwich. So if we're given n and m are those amounts, then multiplying the two together, the product would represent the total possible number of outcomes. And again, it extended into 3 events in the previous problem. So you want to keep in mind that we can continue doing it for however many events there are. So in the following example, the standard configuration for a New York license plate is 3 digits followed by 3 letters. How many different license plates are possible if digits and letters A can be repeated, B cannot be repeated? So let's think about the number of digits we have. So if I count 1 through 9, that's 9 digits. But if you include 0, that's a total of 10 digits we have to select from. And then the total number of letters we have is there's 26 letters in the alphabet. From there, we want to create a license plate where the first 3 are numbers. And we're going to do situation A first, where none of the digits and letters can be repeated, and then followed by 3 letters. So let's think about the first slot. In the first slot, we have 10 digits to pick from. Because we can repeat digits, the second slot still we have 10 digits to choose from, and the third as well. Now we are going to do the same thing with the letters, where in the fourth event of selecting the letter, we have 26 to choose from, and because the letters can be repeated, we're going to multiply by 26 2 more times. And so multiplying all of those together, we get that there is a total number of outcomes in which 17,576,000 different license plate numbers can be produced if letters and numbers can be repeated. Now, in situation B, it cannot repeat. So this is a type of permutation where, let's say the first 3, we have digits. So there's a total of 10 digits. And if one of them is chosen and that can't be repeated, then we only have 9 left to pick from. And then from there, only 8 by the time we get to the third event of selecting the number. The last 3 slots are letters. And for the letters, we have 26 total we can choose from initially, then 25, then 24. And so if we multiply these events together from using the fundamental counting principle, we have 11,232,000 different cases we can, different license plate configurations. You can see it's slightly less than if we allowed the digits and letters to repeat. So the last 3 examples that we have here, the first example, we're going to represent the sample space using an organized list, a table, and a tree diagram. So this is kind of like the longer way of doing the possible outcomes, but it does give us all of our sample space. So the baseball team can either wear blue or white shirts, so BW, with blue or white pants, so BW. In an organized list, what we're going to do is list out all of the possible outcomes given those 2 events. So the event that you select a blue shirt and a blue pant. Blue shirt, white pants. White shirt, blue pants, and then both white shirt and white pants. So we have an organized list of all of our possible outcomes, and lots of times we write it in set notation, so we list it out as such. So that is one possible way of representing a sample space. Another way is using a table where your possible outcomes for the events of shirts are, so for shirts, we have blue and W, so those are our row titles. And then for pants, we have the same selection, blue or white. And so we create a table of values from that and write out all of the possibilities where we take the value from the row and the column to get BB, WB, BW, and WW. And so we should get the same sample space as we did with the organized list. And then lastly, if you prefer a tree diagram, we would write the event of the selection of one of the either shirts or pants. So let's say we pick pants first. We have two options, blue or white. And from each one of those events, given you've selected blue or white pants, we're going to have two strands. So the next event is the selection of the shirts. And so with the shirt, you have a blue or a white option. And so in order for you to collect your sample space, you're going to read, for example, that pathway gives you BB. So our sample space is BB. We have BW and WB and WW. Okay, so that's the event in which you have to come up with the sample space. Those are three different organized ways to do so. However, if they're asking you just to find the total number of outcomes in each situation, you don't necessarily have to do all of that to come up with the fact that that there was 4 possible outcomes. We could have just taken the fact that the event of selecting a shirt was 2, and the event of selecting pants, there's 2 options, so 2 times 2 is 4 possible outcomes. So in the next question where they're asking for a total number of possible outcomes, we're not going to create the sample space, we're just going to come up with how many possible options. So a room is decorated with one of the choice from each category. You can see that you have multiple events occurring here. So then we just take the number of choices and multiply them together using the fundamental counting principle to come up with how many possible outcomes there are. And so if we multiply all of that together, we get 28,800. Go ahead and pause, read 3, and find your answer for that. So hopefully you guys simply just went down and multiplied all these numbers together to find all the different ways that you can come up with your cafeteria meal based off of the choices that you're given there. And so if you multiply all those together, you should get 860.